Right. Hello, everyone. So we are going to wrap up Unit 2 with a lecture all about homeostasis and how bones are involved in homeostasis or balance in the body. So we talked about homeostasis in Unit 1 way back when, and we learned about positive feedback and negative feedback and how balance can be maintained. So we're going to look at an example of negative feedback that the bones are involved in. We just finished talking about joint disorders and bone fractures, so all of this kind of imbalance, and now we'll end with balance. It does a good job of reviewing some of our older lectures in this unit as well, so it's a great way to kind of lead into our unit exam eventually. You can go ahead and title your paper Unit 2, Lecture 6, and homeostasis of calcium in the blood. So as we discussed in the opener, calcium is stored away in bones as calcium phosphate. And we need this calcium in our bones because calcium phosphate makes our bones hard. It gives it that really good structure so they don't break easily. Calcium is also needed in our blood because the blood is a big transport system for our body. And there are many different cells in our body that need calcium for various functions. And so we're going to start off with that. So we can go ahead and write, first of all, calcium in bone is stored away as calcium phosphate, that inorganic portion of bone. And it gives the bone its hardness. Another thing that will be good right here is that it is part of the bone matrix, right? It's that inorganic portion of the bone matrix. So just a reminder there. And we drew this bone matrix in our Haversian systems. It's all the space between lacunae and osteocytes is filled with this bone matrix that those osteocytes continue to keep replenishing. And then our second bullet can be that calcium in blood can be sent to different cells for various uses, such as muscle contraction. So every time we move a muscle, calcium is needed. The movement of calcium ions help our muscles to move, and we'll take a look at that when we get to our muscle unit. The movement of calcium ions across membranes also helps with the function of nerve conduction, which we are doing all the time, sending signals to the body. And another example of where calcium is used is in blood clot formation. Okay, so again, we know that bones have a function of storing salts and storing different materials, minerals, and so here is that function. The calcium is stored in the bone, but it also is needed in the blood, and so we're going to have to keep that balance of building bone up and breaking it down, building bone up and breaking it down, and we know we have our osteoblasts and our osteoclasts to do that constantly. Okay, so the next thing we're going to go into is the feedback mechanism itself, the homeostasis of how much calcium do we want in the blood versus stored away. So I'm going to try and zoom out, but basically I'm going to set up a feedback loop. I'll show you it when it's finished. It's going to go like this. So it's going to take up the entire rest of your page. So right in the center of what you have left is where I'm going to start. And I'm just going to create my boxes first to kind of leave space and then go from there. So, right here, this will kind of be like our home base. This is when we are at normal. And from there, I'm going to take just a different color and draw a box up top. And then on each side, 2 boxes as well. We'll do the same over here. And I'm just going to draw some arrows. So we're going to start off with normal blood calcium levels here. So we're going to look at the amount of calcium in the blood, not in the bone, but in the blood. And we're going to then kind of move through that feedback system where we first look at the stimulus. And then we look at the receptors. So again, stimulus is like what is causing this entire loop to occur. Receptors are what sense that there's a change in the body. Then we have a control center in a feedback loop, which is going to determine what actions to take. And it's going to tell the effector, another part of the body, to do something, do a certain thing based on what it is being told. So this is kind of like our decision maker. It gets information from the receptors, it kind of decides what to do, tells the effector to actually do that, and then we end up with our response, which is usually going to bring us back right to normal. And then we're going to do the same exact thing down the bottom. Just going to use a different color here. And since this is a negative feedback loop, there's 2 directions we can go. So since we're working, actually let's go like this first. We'll add this into the box in the center. Normal blood calcium levels. Okay, so this is going to be like our normal. This is what we want. Normal blood calcium levels, meaning there's enough calcium stored away in bone that the bones are nice and solid and hard, but there's also enough calcium in the blood that it can be used for muscle contractions, nerve conduction, blood clot formation, etc. So we need some of it in the blood so it can be sent to those different cells. So our upper feedback loop is going to be when our blood calcium levels get too high. We have too much calcium floating around in our blood. And then down here, we're going to look at the loop when blood calcium levels are too low. So I should probably draw the boxes first again. So again, we're going to have 1 down the bottom and 2 on each side. Well, these are a little lopsided. Okay, and again, we're going to walk through that in same loop where we have the stimulus, some kind of a change. We have the receptors, which sense that change. We have the control, which decides what to do with that change that's being sensed, and it tells those effectors to do something about it. And finally, we have the response, which brings us back to normal. And our last thing to do is fill this all in. So I'm going to use a pen, and I'm going to start moving upward into our blue boxes with the stimulus. So here, from normal blood calcium levels, what happens is we'll end up with too much blood calcium in our blood. So I'm going to write that blood calcium levels increase. They're high. Okay, and you want to think about like when would blood calcium levels increase? Well, maybe we just ate a meal or drank milk, had something that was high in calcium enter our blood. We absorb all of our nutrients through our small intestine, which then sends them right into the blood, and from there they get sorted and sent different places, and so that's the first place they will go. So maybe we just ate a meal or drank something with calcium in it. From there, we are going to go to receptors. So if we have lots of calcium in our blood, what's going to sense that? And it's going to be cells in the thyroid gland. So cells in the thyroid gland sense the increase in blood calcium. Okay, cells in the thyroid gland sense the increase in blood calcium. If you want to take a second to like go to Google and type in like thyroid gland, it might give you a good visual of where it's positioned, but where it is it's anterior to the trachea, which is like your breathing tube, and so you can find it there, and or it's near your breathing tube, near your pharynx. The trachea is your voice box, so it's like where your Adam's apple would be, that kind of an area. So you can kind of feel that area, and that's where this little guy is. It looks something like this, kind of just like hanging off of your trachea, your voice box. It's like a butterfly shape with like a little, I don't know, it kind of looks like a pumpkin, maybe. I don't know. But there it is. So it hangs off of the trachea. So I'm just going to write that anterior on the front side of the trachea. I probably could have fit that in the box, but oh well. All right, so once these cells in the thyroid gland sense this increase in blood calcium, they are going to tell your thyroid gland to, they are going to decide to release calcitonin. So the receptors are the cells in the thyroid gland, and the control center is the thyroid gland itself. So thyroid gland. And the control center, the thyroid gland, is going to decide to release calcitonin. So the thyroid gland releases a hormone called calcitonin. Now this calcitonin is going to travel through the blood from the thyroid gland to the bones, and it's going to tell the effector, which is osteoblasts, to deposit calcium in the bone. In other words, it's saying build bone matrix. And we know that our osteoblasts are our bone builders. Okay. Finally, from there, we have our response. Since these osteoblasts just took all this calcium out of the blood and they built some bone matrix, the blood calcium levels return to normal. The blood calcium levels return to normal, and there we are, back at homeostasis. Maybe we should write that this is like, well, no, we'll leave it. Okay, back in balance. So some key things here to note is the stimulus is high calcium levels in the blood. The receptor is the thyroid gland. Calcitonin is the hormone released. Osteoblasts are the bone cells involved. And those are some key terms that you'll see are different from our feedback loop down here. One thing that I like to use to remember this, and you can think of your own trick, but I'm going to write it up here in the top left corner, is HTCB. I like to think of the acronym, have the cheesy bread. You're at a restaurant with your friends and they're like, have the cheesy bread. The cheesy bread is so good. Cheesy bread's always good, So I feel like, that'd always be a recommendation someone would make. Have the cheesy bread. Now, all of a sudden, I'm really questioning if that's a Z or a S, but I'm pretty sure it's an S in cheesy. Struggles. Okay, so have the cheesy bread. What does this even mean? It's a trick to remember that if blood calcium levels are high, H, then the thyroid gland releases calcitonin, and the osteoblasts build bone matrix. So the B stands for the osteoblasts. Because osteoclast and osteoblast both start with an O, so I couldn't do an O. So have the cheesy bread, high thyroid releases calcitonin, osteoblasts build. That can kind of help you remember that loop. Now we'll go to the other loop down here. If our blood calcium levels decrease, meaning they're low, here's the loop that would occur. Why would they be low? Well, maybe all the calcium in the blood has been used for muscle contractions. Maybe you were just exercising and all that calcium has been kind of taken in and used in muscle contractions, or maybe nerve conductions, or maybe blood clot formation. It could have been used in those processes, and so it's your body's saying, oh, well, it's too low. We need to get some more calcium here in case we need some more muscle movement and other types of activities. Now here, what's going to sense this is cells in the parathyroid glands. So cells in the parathyroid glands sense low calcium levels, or sense a decrease in blood calcium. We'll phrase it the same way as above. So cells in the parathyroid glands sense a decrease in blood calcium. Now, where are these parathyroid glands? Again, you can Google them. I have trouble putting a picture on here, but I'll try and draw it the best I can. There are 4 parathyroid glands, and where are they? Well, they're actually sitting right on that thyroid gland. So you have 4 of them on that thyroid gland. Okay. Now, these cells in the parathyroid gland that senses are going to tell your parathyroid gland, the control center, to release parathyroid hormone. Or they're going to they're going to signal your control center to make the decision, your parathyroid glands to make the decision to release parathyroid hormone, because your control center is what decides what to do next. So parathyroid glands are going to release parathyroid hormone. Now, parathyroid hormone is going to again travel through the blood just like calcitonin did, and it's going to go to the bones to a slightly different effector. It's going to go tell the osteoclasts to break bone, to release calcium into the blood. Okay. Now just think about this. Your bone cells are breaking down bone to release calcium into the blood. That doesn't mean all of a sudden your bone's gone. Bones are constantly being rebuilt and broken down and replenished to make them stronger as they're used. The more you use and the more active you are, the more you use your bones, the more they'll continue to replenish and make your bones stronger. But if you're not ever drinking calcium, and we'll talk about how vitamin D could affect this as well, then your body is going to say, I'm not intaking any calcium, but I need calcium for muscle movement and for nerve conduction, etc. And it's going to actually wear down at your bone, and it could make your bones brittle and weak, because if you're not taking in calcium, then your body's going to have to take some calcium out of your bones. It's not going to be in perfect homeostasis as one would like. So the response here is our blood calcium levels return to normal. Okay. So again, some keywords here. Instead of being high, the blood calcium levels are low. Parathyroid glands release parathyroid hormone, and osteoclasts are going to be those active bone cells. So my trick to remember this, can you tell that it's lunchtime and I'm hungry, is LPPC. That stands for large pepperoni. You could do pineapple if you don't like pepperoni, but I love pepperoni. Pizza with cheese. So, you're at the restaurant still. Notice this pattern, Italian food, right? You just had the cheesy bread, and now you are ordering a large pepperoni pizza with cheese because low blood calcium levels cause the parathyroid glands to release parathyroid hormone, which then tells your osteoclasts to crush bone. Yeah? So there it is. Normal blood calcium levels can be maintained with these feedback loops, the blood and the bones working closely together, and a bunch of your endocrine glands and hormones, so all interconnected. All right, and that's it. So now you can go ahead and work on the worksheet to just kind of practice this and see how well you know it.